Um, okay, so let's get started. I'm going to share my screen over here. Okay, you should be able to see that. The webinar is called I Square Does Not Tell Us How Much the Effect Size Varies. Now, I assume that most of you are somewhat familiar with meta-analysis. You have either performed a meta-analysis on your own or you've read them. And what you probably know is that virtually every meta-analysis that's published these days uses I-square as the primary index for talking about heterogeneity. For example, they'll say if I-square is low, let's say 25%, that means that the effect sizes do not vary a lot. If I-square is moderate, which is generally classified as being around 50%, that there's a moderate amount of heterogeneity. And that if I-square is high, which is generally classified as being around 75%, that means that there is a lot of heterogeneity. So the first thing, this is just the agenda over here. My first goal is going to be to show you that that is completely wrong. That in fact, I-square does not tell us how much the effect size varies. And I think I'm going to be able to convince you of that in less than 5 minutes, which is saying a lot, given that most of you probably believe that this is true, and you've read, many meta-analyses that tell you that it is true. I'm going to convince you within 5 minutes that that is incorrect. Once I convince you that I-square does not tell us how much the effect size varies, I'm going to talk about what I-square does tell us and how it is meant to be used. After that, if I-square does not tell us how much the effect size varies, then we need a statistic that does give us that information because it's very important information. I'm going to talk to you about the prediction interval, which is a statistic that actually does tell us how much the effect size varies. Another way of saying that is that the prediction interval actually tells us what most of us think I-square is telling us. Now, at that point, I'm going to show you a video of Julian Higgins. I generally teach this course in person rather than online. And my experience has been that some point in the middle of this discussion of I-square, there generally are a couple of people that say, how do we know that what you're telling us is correct? We've read hundreds or thousands of meta-analyses that say that I-square is interpreted in one way, and you're telling us that this is wrong. How do we know that you are right? So once when I was teaching this course, I actually had Julian Higgins attend the course. Julian, of course, is one of the two people that created the I-square statistic. And he actually got up in front of the class and said that everything that I was saying is completely correct. And I have a video of that, and Julian kindly gave me permission to show you that video. And one of the points I want to make is that Julian Higgins and Simon Thompson, who created I-square, agree fully with everything that I am telling you here. In fact, one of the things that Julian says in the video is that while I-square has been cited well over 10,000 times, the vast majority of those citations use I-square incorrectly. Then I have a couple of slides that address the question that everybody wants to know: how is meta-analysis like shopping for jewelry? I think that it's an analogy that you're going to find useful. I'm going to spend 2 or 3 minutes talking about our online workshops that I hope some of you will be interested in looking at. And then we have time for questions and discussion. While I'm talking, I see that most of you have muted yourselves. Please feel free to unmute and raise a question at any point if something is not clear. Okay, so let's get started. The first point I wanted to make is that most papers use I-square as the primary index of heterogeneity. As I said a few minutes ago, if you're familiar with I-square, if you're familiar with meta-analysis, you'll know that this is true. Last night, as I was preparing these slides, I realized I wanted a picture of a paper that uses I-square as the primary index of heterogeneity. I simply went to PubMed, I typed in meta-analysis, and within 30 seconds, I had a couple of dozen examples that I could use. This is a paper that I chose at random. It's a meta-analysis that looks at the prevalence of preventable patient harm across medical care settings. And the person says heterogeneity was quantified by using the I-square statistic. Conventionally, I-square values of 25%, 50%, and 75% indicate low, moderate, and high heterogeneity, respectively. You can see pretty much this exact sentence used in, I would say at this point, literally thousands of meta-analyses. This is the common belief, and it is incorrect. So I want to show you now, I said that I probably could convince you within about 5 minutes that I-squared does not tell us how much the effect size varies, and I'm going to do that using 2 examples from the literature. Here's the first example. This is a meta-analysis that was published in BMJ, the British Medical Journal. It's called Off-Hour Presentation and Outcomes in Patients with Acute Myocardial Infarction, a Systematic Review and Meta-Analysis. The basic idea over here is that obviously when somebody has a heart attack, a myocardial infarction, and they arrive at the hospital, they're going to give them the best care that they can. And this study looked at whether or not it mattered what time the patient arrived in the hospital. And they divided the times into what they call the standard hours and the off hours. Off hours would be people that are arriving in the middle of the night or on weekends, where typically, the people that are covering the emergency room tend to be less experienced, I think, in many cases. And standard hours would be if they arrive during the day when the usual staff is available. And you can imagine that this might go either way. I think one possibility is that if you arrive at the emergency room when the regular staff is on duty, and they are more experienced, that you're more likely to have a good outcome. I guess the other possibility is that if you arrive in the middle of the night when maybe they are less busy, the people that are attending to you might be less experienced, but on the other hand, they might be able to get to you more quickly, and therefore you might have a better outcome over there. So this was a legitimate question. And it turns out that the results look like this. So normally you're looking at a forest plot, which shows each of the studies, and then down at the very bottom, there's one row which shows the summary effect. And typically that is shown as a point estimate with a confidence interval. In some cases, the confidence interval might be a diamond. In some cases, it might be a line like we see over here. But the bottom line is what that is telling us about the average effect, the average across all of the studies. And the confidence interval tells us how precisely we've estimated that effect. People sometimes think that the confidence interval says something about how widely the effect size varies, but that is absolutely incorrect. The confidence interval simply tells us how precisely we've been able to estimate the mean effect. It tells us nothing about how widely the effect size varies from one study to another. So in this example, the mean effect is 1.06. And the confidence interval is 1.04 to 1.09. So what we can say is that on average, arriving during the standard hours increases your chances of surviving. And on average, it increases those chances by roughly 6%. This is an odds ratio, but let's say that it increases it by 6%. Okay, so that's what we know about the mean effect. But what about the dispersion in effects? Does the dispersion in effects look like this? And what I've done over here is I've basically drawn a normal curve to reflect what the actual effect size might be in any single population, right? So we're talking over here, when we're writing up the results of the meta-analysis, we're trying to generalize to all comparable populations. And we need to know how widely the effect size might vary from one population to another. Well, here's one possibility, that, at one extreme, the arriving during the odd hours is a little bit better. Here is an odds ratio of 1.0, and we see that there is a small number of populations where the odds ratio is actually 0.96. That's the number that we see over here. And at the other extreme, the odds ratio was 1.17, which represents, I would say, a very modest effect in favor of standard hours. The key point over here if the distribution looks like this, is that the effect size really doesn't vary all that much. There are, essentially no cases where arriving at night is going to be helpful. And also arriving during the day really doesn't help all that much. In all cases, the odds ratio falls within a fairly narrow range of the mean. And so basically your chances of surviving are essentially comparable, regardless of whether you show up at night or during the day. So if the interval looked like this, that would be the way we would think about the clinical implications of this. On the other hand, what if the interval, what if we're calling this the prediction interval, what if it looked like this? What if there are some cases where the odds ratio is 0.75, indicating that arriving in the middle of the night might actually increase your chances of surviving by roughly 25% as compared to arriving during the day. And at the other extreme, there's an odds ratio of around 1.5, which says that arriving during the day might essentially increase your chances of surviving by 50% as compared to arriving at night. Well, it's a pretty substantial range. And if that turned out to be the case, what we probably would want to do is to look into this and figure out why it is that there are some places where arriving at night is better and some where arriving during the day is so much better. And then let's take a look at a third possibility. Suppose that the distribution of effects look like this. Here there are some cases where arriving in the middle of the night basically doubles the chances that you're going to survive. It cuts the risk of mortality pretty much in half. And at the other extreme, there are some hospitals or some populations where arriving during the day more than doubles the chances that you're going to survive. If there was this much of a range, I think this would be an incredibly important finding, and it would tell us that we really need to figure out which hospitals look like this and which ones look like this. For example, is it the case that the hospitals where arriving at night people do so much better? That's because at night they have a better staff available, in which case that would tell us maybe we want to think about doing that in all hospitals. And maybe the ones where they arrive during the day, they have a much better chance of surviving. That's because they have a better staff available during the day. The point is that once we realize that there's this much variation in effects, that tells us that this is something which potentially could save a lot of lives if we looked into it and figure out what distinguishes these hospitals from these. So these are three possible distributions of effects. Again, in all of them, the mean and the confidence interval is exactly the same. But it's very important from a clinical point of view to know whether the distribution of effects looks like this, or like this, or like this. So which one do you think it is? Now, obviously, with the information that I've given you so far, there's no way of knowing, right? But suppose that I tell you that I squared is 75%. With that information, are you able to figure out whether the distribution of effects looks like this, or like this, or like this? And I will go one step further and remind you that an I squared of 75% is assumed to reflect a high amount of heterogeneity. So based on that, based on the fact that I squared is 75%, which is assumed to reflect a high amount of heterogeneity, does the distribution of effects look like this, or like this, or like this? And what's critical over here is that in the vast majority of cases of meta-analyses that are published, this is the information that is reported in the paper. And so this is the information that people use to get an understanding in their head of whether they're looking at this or this or this. Well, if I can ask you to go to your chat button, there's a chat button down here, and let's assume that those three effects from left to right are A, B, and C, okay? So we're talking here about this is A, this is B, and this is C, and I square is 75%. So make a decision. Do you think it's A, B, or C? And put that into your chat box. And let's see what we see over here. Okay. It actually is one of them, Laura, I appreciate, but in this case, it actually is one of them. Okay, I have a C, a B, C. So I have so far 3 C's and 1 B. Anybody else? 1, 2, 3, 4, 5. Okay, almost everybody signed in. So I have one, okay, 1, 2, 3, 4, 5, 6, 7 people said C, one person said D, and Laura said it's none of the above. Okay, so basically about 90% of you said C. And let me go back to sharing over here. Okay, am I getting, okay. And when I teach this class in person, usually about 95% of the people say C. The actual answer over here, the correct answer is A. And Laura was actually onto something when she said none of the above, and we'll get to that in a few minutes. But I said that within 5 or 10 minutes, I would convince you that I-squared actually does not tell us how much the effect size varies. And in this case, as you can see, people that were given I-squared made the wrong selection. I think what's even more dangerous than that, what's more dangerous than the fact that I-squared does not provide us with this information is that most people think that it does. And this paper was published and I-squared was reported at 75%. And I would guess that of the people that read the paper, more than 9 out of 10 assumed that the distribution looked like this. So the larger problem is that people actually are using I-squared and they're using it to arrive at the wrong conclusion. In fact, I-squared looks like, in fact, the distribution of effects looks like this in this case. What Laura was getting at is that based on I-squared, we really don't have any way of knowing whether the distribution looks like this or like this or like this. And so Laura, you were absolutely correct in that. As it happens, I actually did give you at least the chance of coming up with the correct answer would have been this one, but your intuition is absolutely correct. I-squared does not tell us how much the effect size varies, and therefore there was no guarantee that it was going to be any of these. And let's look at a second analysis. And again, whoever is unmuted, if you could mute yourself, I would appreciate it. Let's look at a second analysis. This is a paper called Restrictive versus Liberal Transfusion Strategy for Red Blood Cell Transfusion, a systematic review and meta-analysis. I'm going to try to stop to mute everybody. Let me see if I can do that. Participants. Okay, so, okay, I guess everybody is muted again. Let's try and stay that way so that it's easier to hear. So this, share the screen, I go over here. Okay, so what we have over here is, this is an analysis of 42, I think it was 42 randomized trials. Patients were in a hospital. They were hospitalized for some particular type of issue. And the question was, what is the best way to use blood transfusions? This is actually something that's come up also recently with COVID, sometimes in the case of using convalescent plasma, sometimes in the case of putting people on ventilators. But there were 2 strategies that were being considered at these hospitals. One was a restrictive strategy, which meant that we will generally not use a transfusion unless the patient meets some very strict criteria, because we're concerned that the transfusion might actually make things worse. And the other option was to say, we will use a transfusion very liberally. As soon as there's any reason to think that the patient might benefit from the transfusion, we'll go in and do it immediately. And the question is, which one of these strategies was better? Patients were actually randomized to one technique or the other. An odds ratio of 1 obviously would mean that the chances of surviving were the same in both conditions. An odds ratio less than 1 tells us that the restrictive use of transfusions, the conservative use, had a better outcome. Patients were less likely to die. And anything to the right of 1 tells us that the liberal use of transfusions had a better outcome. The mean effect was very close to 1.0, and the confidence interval was fairly narrow. So that tells us that on average, there really is no effect. And this tells us how precisely we've been able to estimate the mean. The true mean might fall any place between 0.8 and 1.2. So in any event, using one strategy or the other is not going to have a major effect on average. But again, the question is, what does the distribution of effects look like? If it looks like this, so that, across all of the hospitals that we're looking at, the impact of using one technique or the other, the result was always fairly close to 1.0, that would tell us that, this basically doesn't have any effect on average, and it doesn't have any effect, any major effect in any hospital at all. It really doesn't matter what you do. On the other hand, if the distribution looked like this, where the effects range from maybe 0.7 at one end to 1.3 at the other, that begins to tell us that there is some variation in effects, that there probably will be certain types of hospitals, certain types of conditions where restrictive is better, and some where liberal is better, and maybe it pays to figure out what those conditions are. And finally, if it looks like this, that tells us that there are some types of patients, some conditions where using the restrictive strategy actually reduces the risk of death by about 40%. And there are others where it actually increases the risk by about 60%. And if that's the case, it would be imperative to figure out, what are the conditions that lead to the restrictive approach being much better, and what are the conditions that lead to the liberal approach being much better. So again, we're looking here at the three of them. Let's call that A, B, and C. And now you understand why it would be important to know which of these we're looking at. What I can tell you is that I squared is 29%. And what I can also tell you is that typically an I squared of 29% is assumed to reflect low heterogeneity. So on that basis, are we looking at A or B or C? Okay, I'm going to stop the share. I'm going to open up the chat group again, and I'll ask people to weigh in. A or B or C. Okay. So I have one C. Okay, don't be embarrassed. Another one. Anybody else? Okay. Okay. Okay, Laura is saying correctly, we still don't have enough information to determine this, do we? That's absolutely correct. Okay, well, you guys wised up pretty quickly. Usually when I teach the class in person, the first time I give the people an opportunity to guess at this, about 90% of them get it wrong. The second time, about 50% of them get it wrong and 50% refuse to answer. By the time I get to the third one, nobody wants to put up their hand. So the people in this class have already realized that this is basically you can sort of see where this is going. Let me go back and share my screen. Okay, the answer is that the I square of 29% corresponds to this one. The person with the really correct answer was Laura and the people that put in a question mark, because at this point, I think I've convinced you that I square simply does not tell us how much the effect size varies, and therefore there is no way to know. In this example, this one actually happens to be, this plot actually corresponds to the actual amount of dispersion, but I know that because I went ahead and actually ran the analysis, but there's no way of knowing based on I square. So where are we at this point? In this case, I square was 75%, and the distribution of effects looked like this. The effects vary from 0.96 at one end to 1.17 at the other end, which is a total amount of dispersion of around 21 points. And here, I square is 29%, and the effects vary from here to here, a dispersion of about 107 points. So the amount of dispersion over here is actually about 5 times as much as this one. Nevertheless, I square over here is way smaller than this one. And finally, and equally important, this would generally be classified as a low amount of heterogeneity, where this would generally be classified as a high amount of heterogeneity. So what we're calling a high amount of heterogeneity, incorrectly obviously, is this, and what we're calling a low amount of heterogeneity is this. This would appear to be a paradox. But it's only a paradox if we think that I squared tells us how much the effect size varies. And in fact, I squared does not provide that information. As you know, I think when you went ahead and answered the survey a couple of days ago or yesterday, you were given the choice of, A, B, C, or A, B, C, D, or E. Around 21%, I guess about 20% of people chose any one of the answers. The first question was, can we say that the amount, this would be A over here, this would be B. So the question was, can we say that in the case where I squared was 25%, can we say definitively that there is a small amount of heterogeneity? The answer to that obviously is no, because over here there is a large amount of heterogeneity. The question B was, can we say in the case where I squared was 75%, that there's a lot of heterogeneity? Well, over here I squared is 75%, and obviously there's only a small amount of heterogeneity, and therefore that question was wrong as well. The third question was, can we say that the case where I square 75% has more heterogeneity than the one where I square is 29%? Well, here I square is 75%, here it's 29%. Obviously, the amount of heterogeneity over here is not greater than this, and so that's wrong as well. And since all of those were wrong, then the answer, all of the above, is clearly going to be wrong as well. The correct answer was none of the above. We cannot say that any of these things is true, and about 20% of people got the answer correctly. Okay, so moving back to the actual examples in front of us, what sense do we make of this? Clearly, I squared does not tell us how much the effect size varies. So 2 questions. First of all, what does I squared tell us? And second of all, what statistic does actually tell us what we want to know, which is, does the dispersion of effects look like this, or like something else? So the first question is, what does I squared tell us? In order to explain what I squared tells us, I have to take you back a step and explain that when we're working with a meta-analysis, we're working with 2 distributions of effects. One is the distribution of true effects. That's the distribution of effects that we would see if we actually had a really, really large sample size in each study. So we actually knew the effect size in each study with no error at all, or essentially no error at all. And the observed effects are the effects that we actually see when we take the summary effect for each study. The observed effect is intended to estimate the true effect for each study, but it's always a little bit under that or over that because of sampling error, okay? So we have the distribution of true effects, which is really what we care about. We want to know how much the effect size actually varies from study to study. That's what we want to know. And then we have the distribution of observed effects. That's what we plot in the forest plot. And that serves to estimate the distribution of true effects, but it doesn't get it quite right. What happens is the distribution of observed effects tends to show more dispersion than the distribution of true effects. Why? Well, to explain why, I have 2 slides over here. I'm going to use a hypothetical situation where we draw 5 studies from the same hospital. All studies are based on a random sample from the same hospital. They all are identical to each other in all important respects. And each of those studies is trying to estimate the effect size in that hospital, in that population. So the true effect size in all 5 studies is the same. The true effect size is the actual effect size that we would see if we somehow can include all the patients in the hospital in our study, so that there was no sampling error at all. And let's say, for the sake of argument, that in this hospital, the true effect size is this. What that means, by definition, is that the true effect size in the first study is this, and the true effect size in the second study is this, and the true effect size in the third study, and the fourth study, and the fifth study. By definition, what each study is doing is it's trying to estimate the true effect size in that hospital. And therefore, by definition, if all 5 studies are random studies drawn from the same hospital, then by definition, they're all estimating the same effect. So if we actually somehow could see the true effect size for all 5 of those studies, and we were to plot that, the distribution of the true effects would look like this. It wouldn't be a distribution, it would be a single line, because we're not dealing with the distribution of effects, we're dealing with a common effect. Now, I represented the true effect size by a red circle. What about if we actually go and look at the effect size that we observed in these 5 studies? I'm representing that over here by a blue square. And in each case, I've put a confidence interval around that to indicate that, for example, in this case, the effect size that we observed was -1, but there's a confidence interval around that. The true effect size could fall any place from here to here. Would we expect the observed effect in all 5 studies to be exactly the same? Well, obviously not. I mean, if we ran 5 studies and got exactly the same effect size in all 5 studies, we would know basically that money had changed hands. The whole reason that we do statistics is because we know that the effect size that we observe in any particular study is going to vary from the true effect size. In some cases, it will be lower than the true effect size. In some cases, it might be pretty much the same as the true effect size. And in some cases, it's going to be greater than the true effect size. So if we draw a distribution of the observed effects, it might look something like this. And what we see over here is that the distribution of true effects was basically a single line. The distribution of observed effects is obviously a whole distribution. So the distribution that we're seeing, the distribution of the observed effects, is wider than the distribution of true effects. How much wider will it be? Well, that depends on how accurate each of these studies is. And another way of saying that is that it depends on how large each of the studies is. If the studies are fairly large, so that the sampling error around each study is fairly small, most studies will fall within a fairly narrow range of the true effect. And therefore, the distribution of effects that we get will probably look something like this. On the other hand, if the studies are smaller, so that they have more sampling error and a wider confidence interval, then some of them are going to fall further from the true effect, and the distribution of effects might look something like this. So here's a situation where each of the studies is fairly large, and here's a situation where each of the studies is smaller. And in the case where they're fairly large, the distribution of observed effects is going to be relatively narrow. In the case where there's more error, where the studies are smaller, the distribution of observed effects will be wider. But what's true in both cases is that the distribution of observed effects is certainly wider than the distribution of true effects, because in the true effects, there's no variation at all. And that should be fairly simple to understand in this example, where all of the studies share the same common effect. And that's why I began with this fairly simple example. Now, what's true is, if we move on to a situation which is more common, where the observed effects actually vary, the same idea holds true. So here's a situation where the observed effects fall in this range. There's a small amount of variation, and if we plotted the distribution of true effects, it would look something like this. By contrast, when we move on to the observed effects, the variation is going to be something greater than this because of the additional sampling error. You can see over here that the effects, pretty much fall in the range of maybe -1 to +1, and here they fall in the range of -2 to +2. So if we were to plot this, we would see a distribution that looks like this. But if we plot the observed effects, the distribution is going to be somewhat wider. And again, how much wider depends on how accurate these studies are. In this example, the studies are fairly large. They contribute a small amount of sampling error, and therefore this distribution is a little bit wider than this one. If I move on to the next slide, which I'm calling D, in this case, the studies are smaller. So rather than falling, maybe in the range of -2 to +2, they're going to fall in the range, closer to -3 to +3, because they have more sampling error. The distribution of observed effects looks like this. And whereas in this case, this was a little bit wider than this, the observed distribution was a little bit wider than the true distribution. Over here, it's wider. It is more wide than that, and there's a more substantial difference between this one and this one. So the 4 slides that I just showed you, I had labeled A, B, C, and D, and I'm going to go through them one more time to explain what I square is. I square is the ratio of this distribution to this one. In slide A, where there's no variation over here and this much variation over here, the ratio of the variance here to the variance over here is 0%. It has to be 0% because it's the ratio of true to total variance. If the true variance is 0, then true to total has to be 0. In this example, again, where there's no variation in true effects, the ratio of true to total, again, is going to be 0. So whenever all of the effects are drawn from the same population, whenever there's no variation in true effects, I square is going to be 0. And that is of relatively little interest to us. Where this becomes interesting is when there actually is variation in true effects. So here's a case where the true effects look like this, and the observed effects look like this. The ratio of the variance here to the variance here is 50%. And we would say that I square is 50%. What that tells us, remember, we never get to see this plot over here. We get to see this plot over here. So if I show you this plot, and I tell you that I square is 50%, what you know is that half of the variation that we're seeing over here reflects variation in true effects, and half of it reflects the sampling error that we see over here with these confidence intervals. So half of what we see is true, and if we're seeing this, the true effects actually look like this. By contrast, we move on to the next slide, where now over here, the variation in true effects does not change. Here's slide C, and here's slide D. So we're assuming that the variation in true effects is the same. What's changing is the variation in observed effects. Here is slide C, where the distribution looks like this, and here is slide D, where it looks like this. In this case, the ratio of this to this was 50%. In this case, the ratio of this to this is 25%. So if I show you this, and you think, well, you know, the variation looks like this, I say, wait a minute, not so fast. Only half of that is real. And if you take half of this, you get this. In this case, I show you this and you say, wait, you know, there's a lot of variation over here. And again, I say, not so fast. Only a quarter of that is real. And if you take a quarter of this, you get this. So that's what I square is telling us. It's telling us of the variation that we see, what proportion is real. Okay? And the way that you would compute that, this is another example over here. Basically, what I've done with the red line is I've plotted the distribution of true effects. What I've done with the blue line is I've plotted the distribution of observed effects. And in this particular example, you can see that the true effects range from around 0.4 to around 1.6. And that is a span of 120 points. By contrast, the observed effects range from around 0.15 to 1.85, and that is a span of 170 points. If we take the ratio of 1.20 to 1.70, we get a ratio of 0.71. And of course, you're going to say, wait a minute, you know, 0.71, is that I square? Well, that's not I square. That's the ratio of this span to this span. That's something that I would call I rather than I square. So if I take the ratio of this length to this length, that's going to give me I. The ratio of one standard deviation to the other standard deviation. I square is not a ratio of standard deviations, it's a ratio of variances. So what we need to do is to take that value that we got a minute ago and square it. So we take 120 over 170, and we square that and multiply that by 100, and we get 50%. So in this case, I squared is 50%. And the reason I want to emphasize that is when I show this, and I say that over here, I squared is 50%, people generally say, wait a minute, you know, if I square is 50%, I would expect this to be half as wide as this, and it isn't, it's about 70% as wide. And that's correct. This range over here, this interval, is about 70% as wide as this one, but we need to square that. 70% squared gives us 50%, and that is the value of I squared. So that's what I squared means. It's basically the ratio of this to this. Now, what I want to point out, and now we're starting to get into the really, all of that was sort of background, now we're starting to get into the important stuff. The value of I squared does not tell us how much the effect size varies, because we have to basically take I squared and multiply that by the variation that we see. So here's an example over here where the observed effects vary from 0.92 to 1.08. If I tell you that I squared is 50% and the observed effects look like this, then the true effects are going to look like this. They're going to vary If the observed effects vary over 16 points and I-squared is 50%, the true effects will vary over 22 points. On the other hand, suppose that the observed effects look like this, and I tell you that I-squared is 50%. In that case, the true effects will look like this. And suppose that I tell you that I-squared is 50% and the observed effects look like this, then the true effects will look like this. The point is that I-squared is a proportion. It tells us of the variation that we see what proportion is real. It doesn't tell us an amount. It's not an absolute amount. So what I have over here is I've just taken the 3 plots that I showed you a moment ago and simply spread them out. If I tell you that I-squared is 50% and I ask you how much do the true effects vary, the first thing that you need to know is whether the observed effects look like this, or like this, or like this. If the observed effects look like this and I-squared is 50%, the true effects will look like this. If the observed effects look like this and I-squared is 50%, the true effects will look like this. And if the observed effects look like this and I-squared is 50%, the true effects will look like this. The problem is that when people report a meta-analysis, well, 2 things. First of all, they never report what the observed effects look like because, well, I've been able to compute them over here. It is not something that you would normally compute. It would be fairly difficult to compute. And so we don't know whether we're looking at this or this or this or something else. And therefore, we don't have any way of knowing if we're looking at this or this or this. I think the larger point is that the information that I-squared is giving us is generally irrelevant to anything that we want to know. If I ask about heterogeneity, I want to know whether I'm looking at this or this or this. I really could not care less that this happens to be, some proportion of something else. That really is completely irrelevant to me. The only thing that I want to know is how much do the effects vary? And basically what I want to know is, what am I looking at a span of 16 points or 60 points or 120 points? And I-squared doesn't even begin to address that question. So let's go back very quickly and take a look at the 2 analyses that we were looking at. In the off-hours analysis, I told you that I-squared is 75%. What that means is that if the observed effects look like this, the true effects would look like this. If the observed effects look like this, the true effects would look like this. And if the observed effects look like this, the true effects would look like this. So it's equally likely that I'm looking at this one or this one or this one. I-squared of 75% can correspond to any one of these or anything else. As it happens, the observed effects look like this, and therefore the true effects look like this. And just to show you where that comes from, if you actually go back and look at the analysis, this is what the distribution of effects look like. The observed effects essentially varied from 0.95 at one end to 1.26 at the other. They all fell within an incredibly narrow range. But what's also true over here is that most of these studies were very large and therefore they were very precise. For example, if you look at the study over here, the confidence interval goes from 1.0 to 1.02. The confidence interval over here goes from 0.99 to 1.04. These are very, very precise estimates. And because there is basically, these studies are so large, they introduce very little error into our estimates. And therefore, what we're looking at over here is simply a plot of the observed effects. And you can see they basically range from around 0.95 to 1.26. And because there's so little error added, the observed effects look almost exactly the same. If I-squared is in the range of 75%, the distribution of observed effects is going to be very, very similar to the distribution of true effects, and that is what we're seeing here. And again, the reason that I-squared is so high, I-squared is saying of the variance that we see, where proportion is real, well, 75% of it is real, because since the studies are so large and so precise, they are adding very little error to the equation. So here was a case where I-squared is 75%, but 75% of a very narrow interval is still a very narrow interval. On the other hand, when we move on to the transfusion analysis, I told you that I-squared is 29%. But again, in order to know what that means, you have to know what the observed effects look like. If the observed effects look like this, 29% of that would be this. If the observed effects look like this, 29% of that would be this. And if the observed effects look like this, 29% of that would be this. As it turns out, the observed effects look like this, and 29% of that is this. 29% of a very large amount is still a pretty large amount. And again, to see, where that comes from, if we go back and look at the analysis, the effects, remember in the last analysis, the effects varied from around 0.95 to 1.26. Here we have some studies where the odds ratio was down around 0.5 and somewhere it's as high as 3.28. So the amount of variation over here is several 100% greater than it was in the other analysis. Now, it's true that only about 30% of what we're seeing over here is real, but these are the observed effects, from around 0.5 all the way to, to close to 3. And 30% of that is still a very substantial amount of variation. And this is the variation of true effects. So that's why what we were looking at before is not a paradox. In the case of the off hours analysis, the observed effects look like this. 75% of that is here. And in the case of the transfusion analysis, the observed effects look like this, and 29% of that is here. But what you can see is, first of all, the idea of using I-square as our primary index of heterogeneity is going to lead to results that are seriously wrong. And also the idea that we can then take this value of I-square and say that there's a high amount of heterogeneity is clearly, incorrect. And the idea that we can take the, I-square of 29% and say that there's a low amount of heterogeneity, again, is obviously incorrect. When papers use I-square and classify heterogeneity on the basis of I-square as being low, moderate, or high, they would end up calling this a high amount of heterogeneity and calling this a low amount of heterogeneity. And that obviously is going to be incredibly misleading. And that's why you should never use I-square to classify heterogeneity as low, moderate, or high. A second reason is that, when you say that something is low, moderate, or high, you're talking about that in a clinical or substantive sense. And that really has to be tied to the particular intervention that you're looking at. What I might consider to be a small amount of heterogeneity in one context, I might consider to be a large amount of heterogeneity in another context. And therefore, these terms don't really have any meaning. But that is a separate issue from the fact that, if you wanted to classify them as being low, moderate, or high, you would want to base that on the actual amount of variation. And that's not what I-square is giving you. Okay, if I-square does not tell us how much the effect size varies, what statistic does? Well, that statistic would be called the prediction interval. In this case, the prediction interval, it would be 0.96 to 1.17. Basically, we simply are giving the numbers at this end of the distribution and the number at this end of the distribution. And the reason it's called a prediction interval is if somebody comes to me and they say, okay, I have a situation over here. I'm thinking of, having a hospital. If somebody's going to come into the hospital and we don't know whether they're going to come in at the odd hours or the standard hours, how much of a difference does it make? And I would say, well, it probably doesn't make all that much of a difference. At one extreme, coming in at the odd hours might increase your chances of surviving by 4%. And at the other extreme, it might, at the other extreme, coming in during the standard hours might increase your chances of surviving by 17%. So that's the prediction interval. If they say, well, I don't know which hospital I'm going to, I'm going to pick a hospital at random, what would my chances be? And you say, well, I would guess that the odds ratio for any hospital that you're going to choose at random is going to fall someplace between 0.96 and 1.17. And when I make that prediction, I would be correct approximately 95% of the time, because 95% of hospitals will have an odds ratio that falls someplace within this range. Basically, what I've done is I've given the person the answer that they've asked for. I've simply told them what the range of true effects looks like. I've given the number here and the number here. I think it's preferable, if you can, to display the whole distribution, which gives you a better sense for how the effects are distributed. But just as we can report the confidence interval, which tells us that the mean falls someplace between here and here, we can report the prediction interval, which tells us that in any single population, the effect is going to fall someplace between here and here. How do I get the prediction interval? You can get that with any program that you're working with. Anytime you do a meta-analysis, whether you're using our software, which is comprehensive meta-analysis, or you're using RevMan, or you're using Stata, or you're using R, the program is going to give you some numbers. It's going to give you the effect size, the upper limit of the effect size. It's going to give you tau square, and it's going to tell you how many studies were in the analysis. And I have a program over here which is free. You can download this from the web, and the program looks like this. I'm going to open it up over here. And over here, it asks me what kind of effect size I'm working with. I'm going to click odds ratio, and I click next. I simply have to give 4 pieces of information. For the off-hours analysis, the mean was 1.0639, 0.1639. The upper limit of the confidence interval was 1.0910. Tau squared was 0.0022, and the number of studies was 42. And then I click next, and the program gives me the distribution of effects. And let's see, I probably typed in something wrong over here. Yeah, this was supposed to be 1.0639, and I click next, and it gives me the distribution of effects. And it says over here, it actually writes this out for me so that I'm not going to make a mistake. It says that the mean effect size is 1.06 with a 95% confidence interval of 1.04 to 1.09. And then this is the prediction interval. The true effect size in 95% of all comparable populations falls in the interval of 0.96 to 1.17, which is the same number that I've been showing you before. You can actually go over here and click on File and say, export this to PowerPoint, and the program will open up a copy of PowerPoint and simply drop that in. So it's just as simple as that. Let me come back over here to my slides. Okay, and I wanted to sort of make this point one more time. When somebody publishes a paper, in the case of the off-hours analysis, and they report that I-squared is 75%, you can imagine a group of clinicians sitting around the room and trying to figure out what's the clinical importance of this finding. And they don't really know what it is. I can imagine that one person thinks that the effects all fall within a narrow range, somebody thinks they fall within a moderate range, somebody thinks that they're dispersed widely. They simply don't know. And so rather than thinking about, they're trying to make a decision about how to use this information, but the 3 people sitting here have 3 different ideas about what the information is. They all have their own set of facts. By contrast, if you simply present this, if you simply give them the prediction interval, or better yet, the whole distribution of effects, they're dealing with a common set of facts. They all know what the distribution looks like. Now, at this point, somebody might say, well, if the effects vary within this range, we should take this approach. And somebody else might say, well, if they vary within this range, we should take a different approach. And that, of course, is a discussion that we have to have. But the key point is you want to have that discussion based on a common set of information, which you will be doing in this case. By contrast, if all we present is I-squared, people are not arguing about what's the best way to proceed based on the fact that the distribution looks like this. They're arguing about the best way to proceed based on 3 different ideas about what the distribution actually looks like. And that, of course, is a useless conversation. Let me quickly run through the same thing for the transfusion analysis. In this case, what I would do is actually show you that the effects look like this. How do I get that information? Again, I'm going to go to the program over here. I'm going to go back to File. I'm going to start a new project. And I'm going to say I'm dealing over here with an odds ratio. The mean effect size is 0.9553. The upper limit is 1.1775. The toss squared is 0.0546. The number of studies is 23. I click next. Here I have this. And again, I can simply export it to Word or PowerPoint or any place else. And down here at the bottom, it says the mean effect is 0.96 with a confidence interval that goes from 0.78 to 1.18. And then we have the prediction interval. The true effect size in 95% of all comparable populations falls in the interval of 0.56 to 1.63. And that, of course, is the information that I wanted all along. Okay, so I'm going to close this. Okay, and again, if we are working with this information, people have a common understanding of what the distribution looks like, which of course is what we want. Now, I promised you I would show you a video of Julian Higgins. I'm going to do that now. I've been teaching this class for a while, and I come up with a lot of outrageous things, some bad jokes. People put up with most of it. But one thing that I constantly get pushback on is that people say that I have to be making a mistake in discussing I-squared, because if you look in the literature, and people here who are familiar with, have read meta-analyses are probably familiar that there are, literally hundreds of meta-analyses out there where people say, if I-squared was 75%, that means that I have a lot of dispersion. And whereas, as I said yesterday, it's generally true, is that there is a correspondence. The higher, everything else being equal, a higher value of I-squared will correspond with a greater amount of dispersion. But I-squared really doesn't tell you how much dispersion there is. Because when we say, there's a lot of dispersion, what does that mean? When we're talking about a lot of dispersion, we're talking about this on a clinical or a substantive scale, whereas I-squared is not, it's not on the same scale. It's on a scale of proportions. It tells you what proportion of what it is that you're looking at is probably real. And so it really was not intended to answer that question. It was intended for a very specific purpose, which is to say, of the variance that we're looking at, how much of that is probably will reflect variation in true effects rather than the sampling error. It's an incredibly important function. As I showed yesterday, if you take the variation that you're looking at and multiply that by I-squared, you get the variation of true effects. But that's the way it was intended to be used. And when people say, well, I-squared is 75%, and therefore that means there's a lot of variation, a lot of clinical variation, a lot of substantive variation. It's not the way I-squared was intended to be used. So what I started to say is that I often get a lot of pushback on this. People who are taking the course, they sort of grab me at lunch or at night and they say, you have no idea what you're talking about. You have no right to say that. I've published papers, and I know what and therefore, and I teach a class, and I know what I'm talking about. So what I have over here in the back is Julian Higgins. The creator of I-squared.
Good morning.
Okay. Oh, stand over here. Okay.
Yes, too.
Yes, no, come over here. Yeah.
So you want me to say something? Basically, Michael is right. And we always portrayed it. I-squared, I see it largely as a measure of the extent to which studies agree with each other. And that doesn't matter what their actual results are. And in fact, when we conceived I-squared, we were looking at forest plots, much like the one you had, and we had multiple forest plots. And well, there's something I can see in that without looking at the scale or anything else. It's about the extent to which the confidence intervals overlap. And we want to measure that reflects that. And by the whole notion that we can use I-squared for risk differences, for odds ratios, for differences in means, for prevalences, almost itself argues that it doesn't tell you anything about the actual scale, the actual numbers coming from the studies or underlying the studies. So I just want, Michael, I know, we have 11,000 citations of the paper. most of them are using it inappropriately, sadly. But don't stop citing it. Just use it appropriately. In fact, when we're looking at prevalences like the PTSD, you'll almost always find I-squared higher than 80%. Because studies of prevalence tend to be a bit bigger, so we'll have much less sampling error. And different populations almost all have different prevalences. So we'll see a lot of inconsistency, but that variation in prevalence may or may not be important. And similarly for observational studies, we can get some huge observational database studies that really skew I-squared, even if the actual variation is not very big. When we're looking at randomized trials, which I spend a lot of my time doing at, they tend, compared with other research areas, to be a similar size, not always, but then that's where I-squared has the sort of properties to which we developed it. That is a neat measure of the extent to which studies agree. But my thoughts. I'm very happy to answer any questions or I can get on with the course.
People have other questions?
Okay, so let's see. Okay, so the points that Julian made, first of all, okay. The first point that I wanted to emphasize is that he said over here, Michael is right. He made the point that I-squared cannot tell us how much the effect size varies. In other words, since it's a proportion, if you wanted something that actually told you how much the effect size varies, it would have to be on the same scale as the effect size. It would have to be, you know, a risk ratio of this point to this point, or an odds ratio from this point to this point, or something else. The very fact that it is a proportion, he said, tells you that it's not going to give you an actual amount. He said that it reflects inconsistency, not heterogeneity. This is a point that I think it's important once you get this. This is really has to do with why he created I-squared. And I probably should not take time to go into it now. This is taking longer than I had anticipated, but it's something that we cover in the workshop. I just wanted to say that you know, used appropriately, I-squared is very useful. The problem is, as Julian said, that most papers use I-squared incorrectly. And another point that he made, I might have edited this part out, but he made the point that the estimates of I-squared are often very imprecise. And in fact, that is something that applies to all statistics for heterogeneity. People often compute I-squared and tau-squared and the prediction interval with based on a meta-analysis with maybe 3 or 4 studies in it. If you don't have at least 10 studies in the analysis, all of the estimates of heterogeneity are not going to be reliable. That applies to I-squared, it applies to the prediction interval, it applies to tau-squared. It simply is the way things are. So if you want to get a good estimate of heterogeneity, you simply need a sufficient number of cases. The key points that I would, we're approaching the end, the key points that I would want you to take home from this webinar is, first of all, that if you wanted to use I-squared at all, the way to use it would be to provide some kind of context for the forest plot. So if you look at the forest plot and you're told that I-squared is, you know, close to, let's say, over 80%, you know that the variation that you're going to see if you actually got rid of the sampling error would look something like what the forest plot looks like. On the other hand, if I-squared is low, let's say less than 10%, then most of the variation that you're seeing is simply sampling error, and you sort of need to look at the forest plot in that light. The most important point I would make is that, you know, whether or not you report I-squared doesn't really matter. You should always report the prediction interval, or let me say, if you have enough studies to estimate heterogeneity reliably, you should always report the prediction interval. The prediction interval actually tells us how much the effects vary. And another way to say that is that the prediction interval provides the information that people think is being provided by I-squared. This is the information that we actually care about. The next thing is that these classifications of heterogeneity as being low, moderate, or high are essentially meaningless. Don't just toss them out. Let me see over here. I wanted to point out that there are a number of papers that address the same point that I'm making in this webinar. And these are all obviously peer reviewed, and you can download them from our website. One of them is called Basics of Meta-Analysis. I-squared is not an absolute measure of heterogeneity. The authors are myself, Julian Higgins, Larry Hedges, and Hannah Rothstein. Here's a paper published in BMJ called a plea for routinely presenting prediction intervals in meta-analysis. This was published by Joanna Intout, Johnny Anitis, Mareska Rovers, and Jill Goman. I might have mispronounced that. Here's a paper that I published in the Journal of Physiotherapy called Research Note. In a meta-analysis, the I-squared index does not tell us how much the effect size varies across studies. Two caveats, as I mentioned a minute ago, if you have only 2 or 3 or 4 studies, there's no point in computing any estimate of heterogeneity. They're not going to be useful. And also, if you go ahead now, as I said before, you can download the prediction intervals program from our website, which is meta-analysisworkshops.com. The version of the program that's currently there is simply an Excel spreadsheet. The version that I showed you a few minutes ago is complete, but we are still completing testing on it. Hopefully that will be finished within 1 or 2 weeks. And then anybody that has downloaded, if you go there and download the program, we capture your email address, and I will send all of you an update in hopefully within 2 weeks, maybe even less than that, to the program that I just showed you. Okay, the next question that people always want to know is, how is a meta-analysis like shopping for jewelry? And the answer is this. In a meta-analysis, typically the question that we ask is, how much does the effect size vary? And the answer to that is given by the prediction interval. A second question we can ask is, of the variance that we're seeing, what proportion of that variance is real? And the answer to that is given by I-squared. If this is what we care about, this is the answer that we want. If this is what we care about, this is the answer that we want. And the argument that I am making is that in virtually any time you look at a meta-analysis, this is the question that you have in mind, and this is the answer that you should want. Similarly, if you go into a jewelry store, I can imagine 2 questions that I might ask. I can go in and I can say, I'd like to buy a set of pearls. I can say, how much are the pearls going to cost me? Or I can say, how much of a discount are you giving me? In other words, of the list price for the pearls, what proportion will I be paying? If this is the question that I intend to ask, then this is the answer that I want. And if this is the question that I intend to ask, then this is the answer that I want, right? This question, this answer, this question, this answer. Each question comes with a specific answer. Now, if I go into a jewelry store and I say, how much are these pearls going to cost? And the salesperson says, well, I'm going to give you a 25% discount. You're going to pay only 75%. I understand that I still don't know how much I need to pay. I'm not going to write a check to the jewelry company for 75% and, put in the note over here, for forgetting my anniversary, because I realize that when that gets to the bank, they're going to look at me like I'm some kind of a, like I'm obviously I don't know what I'm doing. You can't write a check for 75%. So if the person says to me, you're going to pay 75%, I'm not going to write the check. Instead, I'm going to say, well, at a minimum, I would say, well, 75% of what? And more appropriately, I would say, well, that does not address my question. I ask how much I need to pay. I need to know the amount, not the proportion. So I understand that if I want to know the amount, I want to know the amount, and I'm not going to take 75% for an answer. I can't write a check for 75%. The analogy would be that if I'm working on a meta-analysis and this person comes in and I'm sitting here and she says to me, how much do the effects vary? And I say, well, they vary by 75%. Typically what people say, well, yeah, sounds good. I'm going to write down that I-squared is 75%. And what I'm saying is that makes about as much sense as writing a check for 75%. What the person should say to me is 75% of what? Or more to the point, they should confront me and say, well, that does not address my question. I need to know how much the effects vary. I need to know an amount, not a proportion. I need to know that they vary from 0.7 to 1.3 or from 0.5 to 1.6 or whatever it is, but I need an actual amount, and a proportion is not going to give me that information. I want to spend just about 2 minutes talking about our online workshops. We do offer, I normally travel around the world on a regular basis offering these workshops in meta-analysis. Because obviously of the pandemic, I'm not doing that anymore. but I have spent the last 9 months taking this course and making it into an online workshop. There are going to be 3 of them, one that covers the basics in meta-analysis, which is available right now, another one which covers intermediate topics, and a third one which covers advanced topics. The course in basic meta-analysis, as I said, is available right now. It includes about 10 hours of video. It also includes, every week we have a series of group discussions on Zoom where people can log in and ask questions. And then also, if there's a question that I don't feel is appropriate for a group discussion, I will contact you and set up a private discussion so that we can deal with any particular questions that you have. If you have any questions or comments for me directly, this is my direct email, biased100@gmail.com. That goes directly to me. It bypasses the office, and I will try to get back to you very quickly. If you're interested in learning more about the workshop or registering for the workshop, it's meta-analysis-workshops.com. And you can look at that, and it actually goes through each one of the videos, explains what is covered, what is not covered, how the workshop works. And I would encourage you to go over there and have a look. I recorded this session, at least I hope I did, and I will send a link to that recording to you so that you can go ahead and look at it at your leisure if you would like to. So thank you very much for your attention. Let me see over here. This took a little bit longer than I expected, but I appreciate your staying with me. I'm more than happy to entertain any questions that you might have right now.